this is numbers 3 and 4 for the example problems. Our task is to calculate the energy, E, of a photon, given that's an L equals 589. The L stands for wavelength. You know from my last set of problems that whenever we have a problem like this, I'm going to change, oh boy, there we go. I'm going to change my wavelength from 589 nanometers to 589 times 10 to the negative 9th meters. I'm going to use C equals this, but instead of finding C, I'm going to actually find frequency. So frequency looks like C divided by wavelength, which means 3.0. Speed of light does not change. 3.0 times 10 to the 8th meters per second divided by 589 times 10 to the negative 9th meters. Meters cancel. I'm left with 5. This is one of the answers from one of the first ones. So I need to find frequency first. I do that because in my next equation, because there's two equations for this one problem, in my next equation, come on, bonehead, 1 over seconds like this, that is frequency. My next equation is going to be energy equals, and that's H, and the H stands for Planck's constant, so n times frequency. So the H is 6.626 times 10 to the negative 34th. That is joules times, that's what that dot means, between the J and the S, times seconds. So I simply plug these two in together, like 5.09 times 10 to the 14th. 1 over seconds, like this. The seconds cancel because it's seconds on top and seconds on the bottom. I'm left with joules. The amount of joules I have for this one photon is very small. It's 3.37 times 10 to the negative 19th, so 3.37. Oh, by the way, I forgot to say something. This right here is in page 222. Let me just check. 223. It's an example problem or a sample exercise or something like that. I forget what it's called. It's in the gray area. Excuse me. Times 10 to the negative 19th joules. Okay, 19th, and joules is how we measure energy. So that's it. That's a pretty easy question once you get good at doing or using this equation here to go between wavelength and frequency. Then you can figure out what frequency is and then plug it into our second equation, which is energy equals Planck's constant times frequency. I got something in my throat here and I don't want to sorry about that. Okay, anyway, moving on to the next one. Now the next one's a little bit more complicated. So for the next one, and this number 4 is actually the example problem that's, where are we at here? Page 229. I'm going to show you how to do this. Let me just make sure I got the right one. So indicate whether the following electronic transitions emit energy and requires absorption of energy. Emits or requires absorption. Okay, so it either emits energy or absorbs energy. So we don't have to do the actual calculation of how much energy. I wouldn't mind showing you how to do that though with one example. I'm going to do that though in the 6A problem set. So look for this in the 6A problem set. It's actually number 36. I'll do one as an example and see if you can do the other two then. And I'll be looking for you to do the other two. There's 36A, B, and C. So I'll show you an example on how to do that in 36A, and then you can fill in the other two by following my example. Okay, so let's take a look at number 4 here. This one's not going to be too bad. Indicate whether each of the following electronic transition. These are just words that make it sound. So if you remember, I talked about the nucleus. The nucleus, okay, looks like this, and then the first electron is in major energy level n equals 1. The first and second electron are there at ground state. second energy level 2 like this, and then for letter A, it's talking about the third main energy level, which would be the third ring outside the nucleus. And if we have an electron that's jumping from A, or for n equals 3 down to n equals 1, that means that it's going from a higher to a lower energy state, which means energy is given off. So if energy is given off, it is emitting. So for letter A, it is emitting energy. Okay, how much energy we're going to find out in our calculations for problem set 6A. So take a look at the second one is from number 2. Let's go to, let me do one more, n equals 4. And if I'm going from an energy level n equals 2 and I'm jumping up to n equals 4, I'm going from a lower to a higher energy, which means that for letter B, we're going to be absorbing energy. Okay, how much energy we're going to find out, like I keep saying. So that's how it works. If you jump to a lower energy level, you're emitting. If you jump from a lower one to a higher one, then you are absorbing energy. And that electron will only absorb as much energy as it takes to go from here, okay, to here. Maybe I should do that in a different color so it looks a little bit better. From here to here, whatever this energy is, that's what it absorbs. If it's given too much energy and it goes from here to here, it will only slide back down to this and only absorb that much energy. Remember the stair-step thing I talked about in 6.3 and 6.4. So electrons only absorb quanta of energy. That's all they do, quanta of energy, which is a specific amount. And that's what we're talking about, stair-step lines, quantum mechanics. Woohoo! Okay.